Good morning. The following Zoom session is being recorded and will appear later today on my YouTube channel, Math with Mayo. There are two different classes that may be observing this session. Therefore, when you participate in the Zoom meeting, if you do not wish for your picture or your name to be made public, please leave the video off and use an alias name. If you have questions during the meeting but do not wish to speak, email me at bmail@ybcc.edu and I will respond as soon as I can. First of all, before I forget, on Thursday, May 27th, I will not be available during my office hour. I have a faculty meeting. If you do have questions during that time, however, email me and I will get back to you when the meeting is over. Also, Memorial Day weekend, I will not be available Saturday or Sunday. So if you get in a panic over the weekend, you'll have to wait till Monday to get a response from me. All righty. Anyway, having said all of that, we're going to go on to section 11.4. So let's get started. We've been looking at exponential functions, and we're going to look at some new kinds of functions called logarithmic functions, which are related to exponential functions, as we will see. But first of all, let's say we had the following. 2 cubed equals 8. And 2 to the 4th power equals 16. What if I said 2 to the x power equals, let's say 11? Looking at this pattern, we could see that x must be somewhere between 3 and 4. Using a calculator and just trial and error, we could say 2 raised to the 3.1 power, 2 raised to the 3.2 power, etc., etc. And through trial and error and a lot of time, we could get however accurate we want it to be. But there's a better way to do that. In other words, what do we do when the unknown is the exponent? How do we go about solving that? Well, if we have the equation 2 to the x power equals 11, there is an equivalent equation that is written as what is called a logarithmic equation. And I'm going to make a two-way arrow here. The following would be true. Log base 2 of 11 equals x. Now, log base 2 of 11 equals x. Initially, that really doesn't do us any good because if we don't know how to deal with all of that, but at least I want to point this out. We have isolated x. So if we could figure out what to do with log base 2 of 11, we could solve for x. And in the rest of this chapter, we'll be doing that, figuring out what to do with log base 2 of 11. We're going to come back to that later. All right, now, let's say we have the following. We have x equals b to the y power. Okay, we could rewrite that as log base b of x equals y. Notice that the three letters x, b, and y are all present in the logarithmic form, but things have shifted around a bit. Now, when we say x equals b to the y power, b is the base and y is the exponent. On the right side, where we have log base b of x equals y, again, b is the base. We say log base b of x equals y. So the base here is the same as the base there. However, on the left side, we have y attached to the b as an exponent. On the right side, we have x somewhat attached to the b, though it's not an exponent. So what we've got is the base here is the same as the base there, but the two other variables or letters change places. I like to think of it as like an inning of baseball. You have players up to bat and players out in the field. After the players up to bat make 3 outs, they change places with the players out in the field. But in the infield, there's the home plate and first base, second base, third base. The bases stay the same. As the teams trade places, the team out in the field doesn't pick up the bases and carry them back into the dugout. We talk about a stolen base, but that doesn't mean they literally take the base and steal it. So the bases stay the same, but the players change places. Again, the base is the same, and the players change places. Let's put this into action. Let's look at a bunch of examples. So let's say we have the following. We have log base 3 of 81 equals 4. It says write each logarithmic equation as an exponential equation. So the base is going to be 3. That's raised to the 4th power equals 81. So the logarithmic equation on the left, the exponential equation on the right. How about this one? Log base 10 of 100 equals 2. Written as an exponential equation, that would be 10 squared equals 100. Let's see here. Log base 6 of 1/36 equals -2. That becomes 6 to the -2 power is 1/36. How about this one? Log base 8 of the cube root of 8 equals 1/3. Writing this in exponential form, 8, oops. Well, I suppose I could spell 8 that way, but 8 to the 1/3 power equals the cube root of 8. Isn't that true? All right. How about this one? Log 0.01 equals -2. There's something missing here. There's no base written. Well, log base 10 is used quite frequently in mathematics, so frequently that it's referred to as common log. And mathematicians like to use shortcut notation because log base 10 is used so often. When it's log base 10, they say, we're just not even going to bother to write the base. So if it just says log, we are to understand that that means log base 10. So going back to our example, log of 0.01 equals -2, that's like log base 10. So that would become 10 to the -2 power equals 0.01. All right, so remember, log is equal to log base 10 in terms of notation. Okay. All right. Let's see here. Now it says, we've got another one here. X equals log base 9 of 81. So that becomes 9 to the x equals 81. How about this one? N equals log base b of r sub 1. So b to the n power equals r sub 1. Now we're going to go the other direction. We're going to take an exponential equation and write it as a logarithmic equation. So here we've got 8 squared equals 64. So the base is 8. So we're going to get log base 8 of 64 equals 2. Now, you might be asking, well, just what is a logarithm? Well, a logarithm is an exponent. Notice the log here is the exponent. How about this one? 10 cubed equals 1,000. So that would be log base 10 of 1,000 equals 3. Note, I could also write it like this. Log of 1,000 equals 3 because there's an implied 10 if I don't put a base in it. Okay, 3 to the -4 equals 1/81. Log base 3 of 1/81 equals -4. Or how about this? M to the n power equals p. Log base m of p equals n. Let's see here. 12 to the -2.6 power equals n plus 1. So now log base 12 of n plus 1 equals -2.6. But wait, there's a problem because all of this needs to be grouped, so we need to put it like that. That's okay. If we write log base 12 of n plus 1, that 1 isn't included in what the log's being taken of, so to speak. So we've got to use the parentheses to group that together. Okay, now we're going to solve some equations by changing from one form to another. In fact, it's not a guarantee, but it's pretty close that when you're solving a logarithmic equation, you're going to change it into exponential form. And when you're solving an exponential equation, you're going to change it into logarithmic form. Happens quite often. So these problems, it says solve for x. Log base x of 9 equals 2. So that becomes x squared equals 9. Well, let's see. We could solve that second degree equation by using the square root property, the property of square roots, taking the square root of both sides. We get x equals plus or minus 3. So x equals negative 3, x equals 3. However, there's a problem. This answer is not correct. How would we know that? Well, let's go back to this situation. Log base x of 9 equals 2. In fact, let's go back to just plain old y equals b to the x. Okay, let's go back to the exponential equations. We said that b has to be greater than 0 and b cannot equal 1, the base, right? Because when it's less than 0 or 0, weird things happen. When it's equal to 1, it just gives us a straight line. The domain x could be what? Let's see. Let's write it in interval notation. So negative infinity to positive infinity, any real number, okay? The range had to be greater than 0. Remember on a graph when we had something like this or like that, the domain was all real numbers, the range was greater than 0. Okay, well, if that's true, let's take this, y equals b to the x, and let's write it as log base b of y equals x, okay? This base is that same number there, okay? This x is that same number there, and let's see, let's go with purple. And this y is that same number there. So what does that mean? Well, using this information, that says that b has to be greater than 0. So that means that the base of the log has to be greater than 0. What else does it mean? Well, if this has to be positive, this has to be the positive, which means you can't take the log of a negative number and you can't take the log of 0. We'll try that in a minute and see what happens. However, this, your answer, can be any real number. So you can get a positive, negative, or 0 answer when you're taking a log, but the base has to be positive, that is greater than 0, and the quantity you're taking the log of has to be positive as well. So how does that apply here? Well, if x equals negative 3, we'd be taking a log base negative 3, which you can't do. So the only solution is x equals 3. All right, let's take a look at some more examples. Let's see here. Log base 7 of x equals 0. Well, changing that to an exponential equation, we'd have 7 to the 0 power equals x. Anything other than 0 raised to the 0 power equals 1. So x equals 1. So log base 7 of 1 equals 0. Let's see here. Log base 4 of 16 equals 2. Oh, wait, doesn't equal 2. My bad. Equals x, it says. 4 to the x power equals 16. Okay, well, let's see. 4 to the x power equals 16. This might be obvious that x is 2. In fact, I accidentally wrote that already, but let's look at another way if it's not so obvious. If we could, let's see, if we take 16 and write it as a power of 4, which we can easily do, we see that 4 to the x power equals 4 to the second power, all right? Because of this, we can then conclude that x equals 2. If the bases are equal, then the exponents are also equal. The proof of that lies in information in the sections that we didn't cover in this class. So you'll just have to take it on faith for right now that it works. Okay, trust me. Okay. All right, now let's take a look at another example. Let's see here. Log base 3 of x equals -4. So 3 to the -4 power equals x. But 3 to the -4 power is 1 over 3 to the +4 power is 1 over 81. So x equals 1 divided by 81. Let's see here. Log base x of 0.001 equals -3. Changing that to an exponential equation, x to the -3 power equals 0.001. Well, earlier I said in an example that if we had the bases the same, then we could assume the exponents were equal. If I take 0.001 and write it as in scientific notation, it would be 10 to the -3 power. Well, here we've got a similar situation of before, but instead of the bases being the same, the exponents are the same. So if x to the -3 equals 10 to the -3 power, then x equals 10. So anyway, so log base 10 of 0.001 equals -3. Keep in mind, we could also write it like this. Okay. Now, on your calculator, and I have the TI-30X2S, okay, over on the left column, there is a button that says LOG, okay? The second function key of that button is 10 to the x. LOG, that button, is log base 10. And if you forget that, the second function button being 10 to the x will remind you of that. Let's take log base 10 of 0.001 and see what we get. So on the calculator, I'm going to push the button that says LOG, and I get this, LOG with a parenthesis, 0.001, 0.001, close up the parentheses, and then push equals, and I get -3. Okay, we'll come back to that a little more, just a bit. Let's see here. How about this one? Log base x of 1 over 1,000 equals -3 halves. Wow. It's too early in the morning for this, isn't it? So this would become x to the -3 halves power equals 1 over 1,000. What could I do to x to the -3 halves power to make it just plain old x? Recall that a power raised to a power, you multiply the exponents. So if I want this to be x to the 1 or just x, what would I have to do? I'd have to raise it to the -2/3 power. Because -3 halves times -2/3 would equal 1, and x to the 1 power is equal to x. So now let's deal with the right side of the equation, where I have 1 over 1,000 to the -3 halves power. Okay, that would be the same thing as 1,000 over 1 to the 2/3 power. I think I said -3/2. I meant it was to the -2/3 power, but now it's to the +2/3 power, which is just 1,000 to the 2/3 power. Well, if we take the cube root of 1,000 and then square the results, we get 100. So x equals 100. So log base 100 of 1/1000 equals -3/2. Okay. All right, let's see here. How about this? It says evaluate each logarithmic expression. Log base 3 of 9. It's not an equation, it's just a statement. But let's say, well, let's make it, or turn it into an equation. Let's say that it equals some unknown number that we'll call box. All right? So log base 3 of 9 equals box. Well, now that we've made it into an equation, we could say that 3 raised to the box power equals 9. But I could take 9 and write it as 3 squared. So now I have an equation where the bases are the same, therefore the exponents are the same. So log base 3 of 9 equals 2. Okay. Log base 6 of 216. Well, that equals some unknown. Changing it to an exponential equation, we get this. But 216, I believe I can write as 6 to some power. Let's see. 216 divided by 6 is 36 divided by 6. So we get what? 6 cubed. So the box equals 3. Log base 6 of 216 equals 3. How about this one? Log base 1/3 of 1/81. Oops, 1/81. Okay. Well, that equals some unknown. 1/3 to the some unknown power is 1/81. But couldn't I write 1/81 as 1/3 to the 4th power? And isn't 1 equal to 1 to the 4th power? Because 1 times 1 times 1 times 1. So we could write this like that. So the box equals 4. Log base 1/3 of 1/81 equals 4 because 1/3 to the 4th power equals 1/81. Okay, now we're going to use our calculator some more. It says use a calculator to find each value. Give answers to 4 decimal places. So that's what? 10th, 100th, 1000th, 10,000. So we're going to round to the 10,000th place. It says log 0.57. Okay, so that's log base 10. I'm going to push the log button on my calculator. And I get log parentheses 0.57. Close it up, push equals, and I get -0.244125144. 10th, 100,000, 10,000th, the 2 would round down. So it's going to be -0.2441. Okay, approximately. Let's see here. Let's do another one. Log of 375.876. So log 375.876. Close it up. I get approximately 2.57504. It goes on, but I only need to go this far. The 4 rounds down, so 2.5750 would be the answer there. All right. Now it says use a calculator to solve each equation. Again, round answers to 4 decimal places. Howdy. Anyway, we'll continue. It says log of x equals 2.8945. Well, there's no base written, so the assumed base is a 10, which means we have 10 raised to the 2.8945 power equals x. And let's see what that is. 10, so 10 raised to the 2.8945 power is 784.33211189. We're going to round here. The 1 rounds down, so approximately 784.3321 would be the answer there. All right. Now, let's see here. Let's take the log of -2. So log -2, close it up, and I get, it says domain error. Remember, you can't take the log of a non-positive number. You can't take the log of 0 or of a negative number. So that doesn't work. All right, let's take a look at some problems, some application problems. All right. This says stocking, as an S-T-O-C-K-I-N-G, stocking lakes. A farmer stocked a lake on her property with 75 sunfish. She was told that with the proper oversight, the sunfish population could be approximated by the logarithmic function f of t equals 75 plus the log of t plus 1. Okay, where t is the number of years since the lake was stocked. So t equals number of years since stocked. Okay, find the number of sunfish you can expect in the lake in 2.5 years. So we're going to let 2 be, or t be 2.5. Okay, so f of 2.5 is 75 plus the log of the quantity 2.5 plus 1, which is 75 plus the log of what, 3.5. So on our calculator, we're going to put in 75 plus the log of 3.5. And let's see here. Where did it go? I left something out of this formula. No wonder. It's supposed to have a 45 right there. That's going to change things considerably. Okay, so let's go back and recalculate that. 75 plus 45 times the log of 3.5. All right, now we get 99.483062. So rounding to the nearest whole sunfish, we would say about 99 sunfish. Okay, let's take a look at another example. It says children's height. So how tall a kid is. The logarithmic function h of a equals 29 plus 48.8 log of the quantity a plus 1 gives the percent of the adult height a male child A years old has attained. If a boy is 9 years old, what percent of his adult height will he have reached? So h of 9 is 29 plus 48.8 log of 9 plus 1, which is 29 plus 48.8 times the log of 10. All right, so 29 plus 48.8 times the log of 10. And we're getting 77.8, and that would be percent. So according to this, a male child who is 9 years old has already reached 77.8% of his adult height. Now, that doesn't mean that that's going to happen to every single male child. That's an average. Okay. All righty. So, things to remember. Log equals log base 10. You can't take the log of a non-positive number. In other words, the quantity you're taking the log of can't be negative, it can't be zero, it has to be positive, and the base has to be positive. So if you've got log base A of B equals C, A has to be greater than 0, B has to be greater than 0. C, the final answer, however, can be positive or negative. But again, get used to this notation. All right, so for tonight's homework, section 11.4, I'll be back at 1:15 with an office hour. Just a reminder, this Thursday, there won't be an office hour, but if you have questions, you can email me. I also will be not available on Saturday or Sunday of Memorial Day weekend. So if you have questions over the weekend, you probably won't hear from me until Monday. Anyway, have a great rest of the day, and I will see you later.